Let's do another example of Taylor's inequality. So we saw in a previous video that the degree 2 Taylor polynomial for 1 over x at x equals 3 is this. So we calculated that before, but you could find it by taking derivatives and plugging in 3 and seeing the coefficients of the polynomial. So the question for this video is, how close is the value of y of 3.5, so when I plug in 3.5 for x here, how close am I to the value when I plug in 3.5 to 1 over x? So for this, I'm going to use Taylor's inequality. I will remind you of what the statement says. The error when I use the Taylor polynomial to approximate the value of the function is got to be less than or equal to m over n plus 1 factorial times c minus a to the n plus 1 power, where this m value is anything that satisfies the following condition. If I take n plus 1 derivatives of my function and then find the absolute value, m has always got to be bigger than that, and that's true for values of x that satisfy x minus a has to be less than or equal to c minus a. So I didn't write down what all these things were, but n is the degree of the Taylor polynomial, c is the number I'm plugging in to my polynomial, a is the center, 3 in this example. So let's write all that down. So in our example, n is 2, a is 3, c is 3.5. So the error is less than m over 3 factorial times 3.5 minus 3 to the third power, where I have to write down the third derivative of my function. So my function is 1 over x. You could take 3 derivatives. I think we did it earlier, but if you take 3 derivatives, I feel like you're going to get negative 6 over x to the 4th. That has to be less than or equal to m. For values of x such that x minus 3 is less than or equal to 3.5 minus 3. So the key in applying Taylor's inequality is finding the value of m. So n, c, and a, those are knowns for the most part. The goal is to find a value of m. Well, if you look at what this condition says, if I take the absolute value, I have 6 over x to the 4th. So that's what this has to satisfy. And when I simplify this, this says x minus 3 in absolute value has to be less than or equal to 0.5. What that means is x has to be in between 2.5 and 3.5. At most, it could be a distance of 0.5 away from 3. So what value of m could I take here? What is the biggest that this can ever be? I need m to be bigger than this for all the values of x I can plug in this range. So I'm dividing by x to the 4th. If you divide by a smaller number, the whole quantity gets bigger. So the biggest that this could ever be on the interval, so the biggest that 6 over x to the fourth can be when x is in between 2.5 and 3.5 is when x is 2.5, the smallest possible value. Again, the logic, I'm going to be dividing by x to the fourth. If you want to make this the biggest it could possibly be, you want to divide by the smallest possible number, which in this case is 2.5. So thus, we can take m to be 6 over 2.5 to the fourth power. Then my function will always be smaller than or equal to that on this range. Okay, so then I'm going to use that value of m back in here and find the error is less than or equal to this value of m, so 6 over 2.5 to the fourth, divided by 3 factorial, and then this is 0.5 to the third. Now I have a handle on how bad my approximation really is. Now if you plug this into a calculator, you will get 0.0192. So at most, the difference between 3.5 in the polynomial and 3.5 in the function is this number. This is the worst possible case of my error when I plug in 3.5 to these two things. The actual error is probably even less than this.